Hello, today we're gonna continue with algebraic geometry codes and we'll see some bounds on the parameters. So let's start with a short reminder. So we started with a curve C, we have some points on this curve and we have a divisor on this curve. So this divisor is just a formal sum of the points, and as before we'll split the divisor into two, namely we want that the support of d prime is disjoint with the points we've chosen before. So these points are the ones where we're gonna evaluate the functions on. So we'll evaluate them on these points. And the second one is just some sum of bi pi, where the bi's are integers. Okay, that's what we have, and then we have an evaluation map which goes from this L of d space to fq to the n by sending f to the n tuple t1 to the p1, f evaluated at p1, and so on up to tn to the bn, f evaluated at pn. And these ti's are local parameters which guarantee us that we don't have poles. So these bi's are the same as these here. And the space L of d, let me remind you what this is. So these are the elements of the function field, which, well, let's call the function field k for now, which satisfy that f plus d is at least 0, and this means just that this is at all. So if we write so that at all points the ni's or bi's are at least 0. Okay, now let's go to the code parameters. So we have, of course, the length, which is just n, so there's not much we have to do about this. But let's start with a lemma about the dimension. So the dimension of the code C. So C is just the image of this evaluation map, and the dimension of C is, we call it k as usual, and this is L of d, which is the dimension of this capital L of d. And how do we prove it? Well, we just look at the kernel and we'll see that the kernel is trivial. So we have an injective map and then we are done. So let's start with something we've already seen before. So we have this f plus d, which is f plus d prime plus sum over these bi pi. We know that this is non-negative. And now let's look a little bit further. So that's what we have always, and now let's take an element from the kernel. So f in the kernel of the evaluation, and this means that for all I n1 to n, we have that ti to the bi f at pi is equal to 0, which means nothing else that the valuation, so we have a discrete valuation at pi of ti bi f is bigger than 0, and we can write this in another way, namely this is bi plus the valuation at pi of f. Okay, that's bigger than 0. And now let's see. So f in the kernel of the evaluation is equivalent to f plus d minus, well, that's plus d prime plus d double prime, so that's just d minus the sum from 1 to n pi non-negative. So why is that? So if that's the case, then we get that also, so here we have this f are just so we have, let's say, nu p of f, so the sum over the p, where p is all points, not just the p1 to pn. And so that's the divisor of f. And now we see that it's in the kernel if and only if we have that this is at least 0 because of this equation here. So we would have, so basically this term comes from this equation here. You can think about it a little more if you want, but because that's actually greater than 0, we can subtract it here, and if we can subtract it here, this will be greater than 0. Okay, now what does this tell us? Well, now we get that the kernel of the evaluation is nothing else than L of d minus the sum of the pi. And well, now let me tell you something more. So we always assume that the degree of the divisor is less than n. So I think we also assumed that in the first video, did we? Not sure, but we'll assume it for now. So so this holds for the degree being less than n. Okay, so that's the kernel. Okay, now let's see. Well, we get that the degree of d minus the sum is less than 0. And from there we get that this, so this is just a result about divisors. So if the degree is less than 0, then the space is 0, so it's trivial. So this gives us that the kernel is trivial. So that's the proof of this lemma. If you want, you can think about this implication a little more and prove it as an exercise. So that's this here piece. That's quite useful often, that if the degree is negative, that this L of the divisor is just 0. Okay, now let's continue with a bound on the minimum distance of the code. So d is the minimum distance, and I claim that it's at least n minus the degree of the divisor. And again, we assume that the degree is less than n. Well, if it was bigger, we wouldn't be in trouble anyways, because then it would just say it's non-negative, which is always true. But let's prove it now. So let's take a code word and let's let it be the evaluation of some f. So that's in the code, and we want it to be of weight d. And if it has weight d, well, we know that n minus d positions of c are 0. So at d positions it's non-zero, and at n minus d position it is 0. So let's take these n minus d positions. So this I1 to In minus d are just these positions. So namely, we want to have t I1 to the b I1 f evaluated at p I1 is 0, and so on up to t In minus d b In minus d f evaluated at p In minus d to be 0. And so similarly as before, so before we had it for, let me show you, when do we have it? Yes, so this equation here, or inequality rather, this followed from all the pi's being 0. Now we have the same true for, so now we get the same inequality, but just not all pi's, but just the ones at which is 0. So we get f plus d minus the sum k equals 1 to n minus d, and then p I k is non-negative, so it's at least 0. And now we just apply the degree to that. So we get degree of f plus degree of d plus the degree of this thing here, which is just minus n minus d, is at least the degree of 0, which is 0. The degree of f is also 0. So I don't know if we haven't proven it. I don't know if I mentioned it, but the degree of all elements of the divisors of an element in a function field is always 0. And so we use that. And from here we get that d, so the left-hand side is just d plus the degree of d minus n, and the right-hand side stays the same, and so we get that d is at least n minus the degree of d, what we wanted to prove. Okay, that's it. That's what we wanted to prove. That's also what I wanted to cover in this video. So in the next video about algebraic geometry codes, we'll probably see we'll see that the code parameters depend, and not just the parameter, actually the equivalence class of code. So next time I just mention monomial equivalence, tell you what it is, and we'll see that I'm not sure if I mentioned it in the first video, but we'll look at the divisor. We look at the divisor class of the curve, and we'll not look into it in much detail, but we'll show that an equivalent divisor, so this will be divisors modulo principal divisors, and that if we have equivalent divisors, which means they differ by a principal divisor, then we get a monomially equivalent code, which implies especially that the minimum distance and dimension are preserved. So that means that we don't have to care about divisors, but just equivalence class of divisors. Okay, that's it for today. Have a good day and bye.